So first I wanted to start off with talking about photodynamic therapy. So photodynamic therapy, or PDT, has been shown to have great promise in cancer treatment, and it consists of three fundamental components. So photosynthesizer agents, a light with an appropriate wavelength to activate tumor-localized photosynthesizers, and generation of reactive oxygen species for cell and tissue destruction. So it first starts with administration of the photosynthesizer and allowing it enough time to accumulate into the tumor before localized laser irradiation of the tumor site. And this causes photochemical effects to occur within the tumor, where there is generation of reactive oxygen species such as cytotoxic signaling oxygen, which can cause cancer cell death and lead to local tumor ablation. And PDT offers many advantages over conventional cancer therapies, as it's minimally invasive, causes little to no scarring, and it's a highly localized treatment for more targeted and precise tissue damage. As well, the same target site could also be treated multiple times if needed. And when designing or selecting a photosynthesizer for PDT, you want one that has a high specificity and selectivity for the target tissue. You also want it to have a strong absorption at a specific wavelength and be able to efficiently generate reactive oxygen species for tissue destruction. Now, porphyrin is a very common photosynthesizer that can be found everywhere in nature, and examples of this are chlorophyll and heme. It also has the ability to chelate various metals, which allows it to be used in various biomedical applications, such as for PET imaging or for radiotherapy. And porphyrins are also intrinsically fluorescent, and they exhibit a strong fluorescence from around 650 to 750 nanometers, which falls into the wavelength range that can allow for deeper tissue penetration. And porphyrins can also generate ROS upon laser irradiation, which is an important determinant of PDT efficacy. Now, our lab has designed porphysomes, which are self-assembled liposome-like structures composed of pyrolipid monomers containing a high density of porphyrin in the structure. And it's also non-toxic and can be used for PDT and fluorescence imaging when the particles are uncrunched and dissociate into its monomeric pyrolipid components. And although porphysomes are promising agents for PDT, as it can deliver a large quantity of porphyrin, it has limitations as it's very inefficient and low intracellular uptake in cancer cells and has a slow activation, which could hinder its PDT efficacy. And our lab has discovered that incorporating EDTA into the porphysome structure may allow us to overcome these limitations. So EDTA has been approved for treating heavy metal poisoning, and it's used for various antimicrobial studies, as it's known to increase the membrane permeability of gram-negative bacteria by chelating divalent cations on the bacterial cell membrane, such as calcium and magnesium. And our lab discovered that incorporation of EDTA into the porphysome structure can allow us to take advantage of EDTA's ability to permeabilize the membrane and improve the uptake of porphysomes. So therefore, it shows increased antimicrobial activity upon exposure to light. And we also serendipitously found that after incubating cells with these NPS nanoparticles, they also demonstrated enhanced cellular uptake in cancer cells compared to regular porphysomes, which I'll show in the subsequent slides. And this may also potentially allow for earlier in vivo fluorescence tumor imaging. So here you can see the morphology and size of these particles, and they're very similar to conventional porphysomes in that they're bilayered vesicles, approximately 100 nanometers in size. And as the goal is to apply these nanoparticles in vivo, the serum stability of NPS compared to porphysomes was also assessed. And although it's not as stable in serum compared to porphysome, it still maintained relatively good stability where the particles remain 80% quenched and therefore intact after 24 hours in serum. And to investigate the effect of EDTA on porphysome accumulation in vitro, you can see above an overview of the experimental workflow to quantify the uptake via fluorescence in KD cells. And if you look at the graph on the bottom left, you can see that NPS had the highest intracellular uptake compared to porphysomes at all time points, and it has significantly higher uptake occurring after 6 hours of incubation. And from the fluorescence microscopy images, we can also visually see that NPS has a rapid uptake as well as a rapid fluorescence activation upon entry into cells. Now, temperature modulation is a commonly used method to non-specifically inhibit active cellular uptake pathways. And many forms of endocytosis are known to be temperature dependent, and studies across multiple different cell lines found that there are two temperature inflection points where endocytosis starts to and becomes inhibited. So at around 20 to 27 degrees Celsius, studies have found that fluid phase endocytosis and receptor-mediated endocytosis starts to become inhibited in cells, where the endocytotic rate starts to be reduced within this range. And at temperatures below 10 degrees, lipids in the cell membrane undergo a phase transition from a liquid phase that's more fluid and disordered in its structure to a more rigid gel phase. And at this point, this is where both receptor-mediated endocytosis and fluid phase endocytosis are inhibited. So here you can see fluorescence images of KB cells incubated for 3 hours at various temperature conditions with NPS or with transferrin, which is used as a control, as it's known to be uptaken via receptor-mediated endocytosis. And a comparison of the fluorescence signal between the three temperature conditions shows that the uptake of NPS is reduced at 18 degrees Celsius, where there's very little fluorescence signal that can be seen at this temperature condition. And at 4 degrees Celsius, there's little to no fluorescence signal observed for NPS-treated cells. And therefore, this result suggests that NPS uptake in KB cells are temperature dependent, and they're likely to accumulate in cells via an active process. Now, this was also further confirmed using sodium iodide and 2-deoxy-D-glucose to create ATP-depleted cell conditions. And as you can see in cells that were pre-incubated and co-incubated with sodium iodide and 2-DG, there was a significant reduction in the fluorescence signal of NPS. And this suggests that the rapid uptake profiles of this particle is accomplished through an active ATP-dependent transport pathway. Now, to look into its in vitro PDT efficacy, here you can see the blue bar represents our NPS nanoparticle compared to the purple bar, which is our conventional porphysome. Now, 0 joules per centimeter squared light dose is used to evaluate the potential dark toxicity of these nanoparticles. And basically, cells are kept in a dark environment after incubation with either NPS or porphysomes prior to measuring their cell viability. And what we observe is that NPS has very minimal dark toxicity in PDT-treated wells. What we see is a significant reduction in the cell viability of cells that are treated with NPS compared to porphysomes. NPS basically exhibited significant photocytotoxicity compared to porphysomes, even with a short 3-hour incubation in KB cells when they're irradiated with the 660 nanometer biotable light box, as you can see on the graph on the left-hand side. And what we also observed was that as we increase the nanoparticle cell incubation time up to 24 hours, we see a significant increase in cell killing post-PDT, with over 95% cell killing after 24 hours of incubation. And before wrapping up my presentation, I want to give acknowledgement to my graduate advisory committee, as well as all the Zheng lab members that helped to support my studies. It wouldn't have been possible without them, especially my supervisor, Dr. Zheng, John, Lily, and James Boo. And in conclusion, we basically discovered and developed a new generation of porphysomes called NPS that incorporates a novel EDTA-mediated strategy to potentially enhance their intracellular uptake in cancer cells. And NPS also appears to be uptaken into cancer cells via an active transport pathway, but the specific mechanism is currently unknown, and it doesn't appear to be through a previously well-established target-specific or receptor-mediated mechanism. And through enhancing the intracellular uptake of porphyrin via NPS, it has been shown that it's been able to exhibit higher in vitro PT efficacy compared to the conventional porphysome. And some of the current and future work includes further understanding the specific mechanism underlying the uptake of NPS, as well as investigating their in vivo biodistribution and in vivo PDT efficacy compared to the conventional porphysome. Thank you, and I'd like to open the floor to any questions.
Great, thank you, Tiffany, for a wonderful talk. At this point, as with the previous talk, we'd be happy to take any questions. So again, please raise your hand or type them out in the question box. Well, in the meantime, I do have a question. So in your cell uptake, your cell inhibition studies, I should say, you mentioned you used both sodium azide and 2-DG to inhibit cell transport pathways. So why both?
Yeah, so basically the two major ways that cells generate ATP is through glycolysis or through oxidative phosphorylation in mitochondria. And these two, so 2-DG and sodium iodide, inhibit ATP generation through different mechanisms. So sodium iodide inhibits the cytochrome oxidase in the mitochondria, which decreases the ATP generation via this pathway. And 2-DG on the other end is an analog of glucose, and this is able to inhibit glycolysis, which also helps to reduce the ATP generation and create our ATP depleted cell conditions.
Great. I see Leah has raised her hand, so go ahead.
Thanks, Wesley, and thanks, Tiffany. So why is it necessary to wait 24 hours before measuring the in vitro PDT efficacy?
Yeah, so if we were to actually measure the cell viability immediately after we've irradiated these cells, what you'll find is that you won't actually see much reduction, if any, in the cell viability immediately after PDT. You would have to wait for a certain period of time, as apoptosis is actually a time-dependent process. So that's why we wait about 24 hours for us to be able to get a good measurement of the PDT efficacy in cells.
Great, thank you.